Hi everyone. So you're among the privileged ones. You get some insight into the network stack that Flink is using for communicating between the task managers. And I will show you how it is in Flink 1.3 and the things we were planning and our ongoing implementations for 1.4. So let's start with the current state of the network stack to get started. So this is basically the view that all the operators expect. So whenever you have a subtask on task manager, let's assume on this one there are two, and they're communicating with another task manager, and if something like a key buy in between, so you shuffle data around. So what an operator thinks it's getting is like, this is a single TCP channel, this is another one, and this here as well, and as well. But this is not how it's done underneath, because that would be quite some TCP channels to open. So we're not doing this. Instead, this is how it looks underneath. So we're basically multiplexing the different logical channels into a single one. So in here, we have the same subtask 1 and 2, which are sending data through to the other task manager with subtask 3 and 4. So on the sending side, we do have, like, whenever you emit a record, it's been sent to the record writer that is serializing the record into a byte, into bytes. Then this record, the serialized record, will be sent through the channels to the receivers. So we do have one queue for buffers that go through into the subtask 3, and another one that goes through for the subtask 4. And those are called subpartition queues. So same for the other sender. On the receiver side, this multiplex channel will be reassembled so that we do get what we logically wanted. So that this subpartition queue to 3 will go to task 3, and 4 will down here, and so on. So how do records flow? Let's get a bit more deeper. So whenever a record, when checkpointing is enabled. So whenever a checkpoint barrier comes in, it hits a record writer. The next thing it needs to do is flush all the remaining serialized data. So all the buffers get sent through the subpartition queues. Then the checkpoint barrier itself is emitted into those queues. And then all of them are sent through the netty TCP channel towards the target. So that's, we have them all in the channel net. In the next step, the sender will poll this TCP connection and then get an event one by one. So those records, sorry, one by one. So they will flow into the input channels where they belong. And this is, like, in this input channel 1, we got the checkpoint barrier from the subtask 1. So whenever we read this, we do need to align the other input as well, so from the subtask 2. If we want to checkpoint, we want a consistent checkpoint among all the nodes in the system. So what we do when we read this, we basically pause this channel and then wait for the checkpoint barrier to arrive on the other side as well. And this is when we take a checkpoint. So how do we do this pause? Well, basically, we don't have much, we don't have many options there. We do still receive the events, the records, sorry, and we simply flush them into disk. And so this is called the checkpoint alignment. So there's one thing. And this, of course, stalls and at some point, but we do have some other things. Like what happens, like in here we do receive buffers from netty. This is netty buffer space. But we do want to finally get into our buffer space. So we do acquire buffers from our so-called local buffer pool. But what happens if all of the buffers in there have already been taken? I mean, there is this point where like the reader is not reading fast enough, so all the records go in here, and the buffer pool will be empty. So what's happening then is like the channel is being stalled, and backpressure, that's basically backpressure which kicks in because it's based on the buffers. And if we don't have any buffers anymore, we're not reading from the channel anymore, and we cannot read checkpoint barriers either. So this is a problem we want to solve. So one more thing on the sender side. This is this talk is basically twofold. First is the flow control that we touched before, and then there's network buffers themselves. So on the sender side, I hid some details in the slides before. So we do have one global buffer pool, the network buffer pool on each task manager. And then each subtask gets its own local buffer pool that basically reserves some of the buffers from the global one and offers them to the subpartition queues. So whenever we have a record coming in, we serialize it into bytes, and then we want to send them through at buffers of a specific size. So this is the memory segment default size is 32 kilobytes, and we basically slice this serialized byte array up into buffers of this size. So we take a buffer, then we copy contents from our serialization buffer into it, and then we're sending it down the stream into the subpartition queue until Netty picks it up. We tell Netty, of course, that there's one available. So we do this for the remaining ones. And now there's the thing. We might not have serialized data which is aligned with this 32 kilobytes, which is natural. There will always be something that is not really filled. So we do copy it in there, but we have a buffer that is only half full. So what do we do with this buffer? We could send this partial buffer right away. This way, latency will be very low because it's sent right through when it is there. But it's not optimal with regards to throughput, because we waste some space in here. We could serialize other data into it. So this is not really the way we go. The other option would be we could wait for the buffer to become full. But then we don't know when the next record comes in. So we don't know when we actually want to send it. We could have an arbitrary delay, which you also don't want. Oops. So this occurs at high latency, although full throughput. So what Flink 1.3, and before as well, does, it also has a so-called output flusher. So this half-full, this partial record is basically sent whenever it is either full by adding additional records to it, or when a timeout hits. And this is what the output flusher does. So every, by default, 100 milliseconds, it flushes this partial buffer into the queue. So then you have an upper time limit on the latency. You can configure it yourself. Default is 100 milliseconds. And so you can basically decide whether you want low throughput, whether you want low latency or high throughput. So let's go back to the first one. That's the Flink 1.3. So now we're talking about changes that we want to do, and they're currently underway for Flink 1.4. So let's consider the problem we had before. So this input channel's record reader is not reading records as fast as they got sent through the network. So we took all the buffers from the buffer pool, and now an event comes in, and we cannot place this into our buffer space because we don't have any buffers. So this is obviously something we want to avoid, because this will stall the whole channel. So we do want to never block there. And this is how we will do it. So we were thinking about a credit-based flow control system that basically in an input channel itself is getting buffers proactively from the local buffer pool. Then when it has those buffers, in this case 2, that are free, it will basically advertise this credit towards the sender. So say, oh, hey, Task Manager 1, I do have 2 records that you can use. And this task manager will then know that there are 2, and it can send 2 of those. Whoops, I had the wrong button. Can send the buffers right through, and we know it will not stall in here because we already reserved the ones there. And what it also does, this task manager sends its backlog size, so the number of buffers that it has in queue, so that once we receive it on the receiver side, we know how many buffers we'll need for future messages. We know that task manager 1, in this case, has 6 buffers that it wants to send to us. And if we are able to acquire this many buffers, we do acquire them first, then announce the credit, and then it gets sent through the same way. All right, so what do we gain by this? Basically, we don't have messages on the wire that the receiver cannot handle because it doesn't have buffers. So whenever a single channel cannot block a whole multiplexed input anymore. Also, we have more fine-grained backpressure control. And we improve the checkpoint alignments that we talked before earlier. And what are the costs? Well, basically, the costs are negligible. So only those announcement messages, and we'll just piggyback them with some integers that can send through. And so this is for free. And this is where we continue to the next one. So second one is we want to have this event-driven network. We don't want this output flusher anymore. So before we had the Variant 3, which is the output flusher. That's this system. But what else could we do? Well, instead of having this wait for the output flusher or for another record, we could just insert it into the queue. And from this queue, there are 2 options. Either the network channel is fast enough, so it's already like reading the ones that are in the queue, and then reading the partial one, then it's sent through. Or it's not fast enough because it's busy with some other task, and then the record writer can still write into it. So we have this, whenever the network is fast enough, it will get sent through. We have low latency. And if it's not, then we can wait for it to fill up by the record writer. So this will be the same, will be shared. And then we have the most of the throughput. And we did implement some early prototype, to be honest. And I want to show some few results of this. So consider you have a very slow source, like 1 event every 100 milliseconds. We do have 4 task managers, and it's as simple as the program isn't doing much, emitting a tuple, and then doing some simple map. So we do have a very slow source, as said. And with Flink 1.3, you can decide on the buffer timeouts. So those are 3 values we have around here. And this is the latency that is achieved by this simple, it's called benchmark. So whenever we have a buffer timeout of 0 milliseconds, events are sent right through. So we do observe a latency that is, of course, quite near to 0 as well. This is the red line. And the higher we get, the higher the latency, as expected. With the event-driven flushing, we basically remain at this 0 latency level. Because events will be sent through, and there's nothing else blocking the network, and latency is 0. So what about the throughput, you say? And this is where there's still some work to be done, to be honest. But with Flink 1.3, if you have a 0 millisecond timeout, then you only have very few throughput. So it's very low. It's like in 250,000 in this regard. Whereas the higher the buffer timeout gets, the more it is waiting for the full buffers. And when they're full and only sent when they're full, the overhead is very low. So we get like, what is that? 250,000, like 10 times as much throughput. So with the prototype we have so far of the event-driven, we're kind of in between. We do have a 0 latency, as we showed before. And the throughput is not yet where we want it to be. We do want to get up here, and we're pretty sure we'll get there. So what do we gain by having this event-driven flushes? Basically, we only flush on the network channel availability. You don't have to configure the maximum timeout you want to get. You don't have to make this trade-off between latency and throughput. We do have a near perfect latency behavior and an expected, like, negligible downside on the throughput once done. And yeah, I think I'm through a bit early. So thanks. So are there any questions?
Yeah, thanks for the talk. How quickly do you update the credits? You mentioned that you piggyback them on some other message. Could you repeat what messages that are?
Oops, sorry. How quickly? Well, we do have, let's get to the point. So this is where we got, right? So, I mean, we do have the backlog here, so this node already knows how much it needs. So then it immediately requests the buffers and sends it over. What do you mean by how quickly?
You have the channel credit from the other side, right? You need to announce the credit. So how often do you announce the credit? Like in what interval or?
Well, it's not an interval base at this point. We do have, like we will have a certain amount that each input channel reserves for itself, and somewhat shared. But basically, it depends on the backlog of the sender.
Okay, just because here the receiver, you have 2 buffers free, right? And then the receiver tells the sender, okay, we have 2 buffers. Mm-hmm. So my question was, how often does the sender tell the receiver, that's the number of buffers that I still have available, please send me those buffers?
Maybe I got it the wrong way. So at first, the record will go into the sender. Right. Then the sender will announce the backlog, and then, so it's kind of in the flow at this point. Or am I getting it wrong?
You can think about it the following way. Whenever the receiver side decides to allocate a buffer, you can actually just assign the credit value there, and then whenever the network has the ability to transfer a message the other way, you pick up the current credit value. So it's actually the exact same mechanism as in the second part, right? Whenever the network has availability to transfer something forward, like records forward, in this event-driven model, it transfers a record forward. Whenever it has the ability to transfer a credit message backward, it transfers a credit message backwards with the full credit that has currently been like allocated to channels, like as one message, like when the availability is there. That's kind of the why those two go together. Does that kind of make sense? Yeah. Thank you.
Thanks, Stefan.
You have here a one-to-one relationship to the channels, where you do basically, if you have multiple tasks, sending to the same next task. Is this done on a different level, or is it also done on that? Because then you can come into problems that you have to sub-split your credits across the multiple senders.
No, actually, this is like the 2 channels I showed before. It's basically a mapping, like this channel 3 here that maps onto 3 here.
Okay, this is always a one-to-one relationship. Yeah. Okay.
Any other question?
I think there.
Thanks for the talk. It was really interesting. So I wonder, you said that right now you would, in the old outpush flasher way, you could configure between low latency and high throughput, basically. But right now, your measurements also show that it's a straight line, so you cannot really configure it. But you are aiming to have as high throughput as you could achieve with the old output flasher, and as low latency as possible. So. Is it, or what are, I know those are technical details, but what is the sketch of the solution to actually achieve that? Because for me it seems like at least you gotta have some trade-off, and it's not magically possible to solve everything.
Well, to be honest, what do we have? So we basically, the goal is, I mean, not just to get the best out of the 2 worlds, but also to remove this configuration, because we want to have this value based on what the network is able to offer you. And this is what the nice thing is about this idea. So whenever it can send something, please send. There might be some computational overhead of sending smaller buffers and not accumulating them, but we expect them to be low. and this only affects the throughput at this point. So actually, we do expect to gain the best of both worlds. Yeah.
Hello. Yeah. Thank you for the talk. I was wondering, isn't something very similar, the credit stuff, similar to what reactive streams in Akka is? Like, asynchronous boundaries. I don't know if you are aware.
Familiar.
Okay.
To be honest.
Okay. So don't worry. we can
talk afterwards. Yeah, that would be interesting to see.
Any other question?
I think there's one behind the bar.
Hi, thank you. I was just curious how far down the stack, effectively, how far into TCP and so on you're tuning? Are you just working at the Akka socket layer, or because there's a lot of optimizations built into TCP about retry and window scaling and so on that are useful in some of these contexts, but I don't know if the application is working that far down.
Actually, this is not going through Akka. So we only use Akka for RPC messages, and we use Netty for delivering the data, so for big throughput.
Any other question? Okay, I have one question about the network buffer. Like, is it available for the user to decide the size of the network buffer, or is it already?
No, you can decide the size of this. Would I get the global buffer pool? Where do you have it? Anyway, this is a configuration parameter you can change in Flink. Okay. It's been recently changed for 1.3, so you can have this whole network buffer pool assigned like 10% of your RAM that you have available, or if you decide for a fixed number of buffers. So this is something you can configure.
Right.
Also, like how many of those buffers go into here, or basically how many buffers are per queue. But this is probably about to change.
Okay, thank you. Let's take our speaker. One more question.
Do you support EPOL native transport on Linux with Netty?
EPOL is there. There's so this is inside Netty. So we do have this EPOL loop, one Neo loop for the rest, and for local communication, there's also a path. So yeah, you might need to configure it, right? Not sure. Not sure. Is EPOL chosen automatically, or was that a configuration parameter? Yeah, so you might need to look into enable. Yeah.
Okay, let's take our speaker.
Okay, thanks.